Thanks everyone for coming. My name is Matt. I'm here to talk about JAX, the core JAX project, tell you a little bit about what we've been working on for the past year and some hints about what we're working on next. So yeah, I assume if you guys made it here, you probably know what JAX is. But in case you don't, this is JAX in one slide. JAX is a numerical computing library that you use to write NumPy-like programs and then transform those numerical programs with things like compilation, automatic differentiation, batching, etc. And you can use those. You can run those programs on your laptop, or you can run them on your GPU cluster or your TPU supercomputer, wherever you like. So what I think is exciting about JAX is the things that everyone's building with JAX. So JAX, for example, is used for all the training and post-training and serving of Gemini 2.5. This slide is a little bit out of date. We could also say Gemini 3, but also things like vision and graphics research or world models like Genie, robotics, VO, all this stuff. But there's exciting large-scale machine learning happening outside Google as well. JAX is actually used a ton at Anthropic to build and serve Claude. It's used at XAI for their large-scale pre-training. It's used at Apple. It's also used at places like SSI, and there may be some folks from these places here today. So JAX is really doing a ton of large-scale machine learning. It's also powering this project called Marin, which I think there's a talk on later. This is like a truly open source LLM research program, not just open weights, but just the whole training process and all the code, all the details are open source. Really awesome work from Stanford that we're happy to that JAX is powering. It's also doing things beyond sort of like the bread and butter machine learning. JAX is used for computational biology, like in AlphaFold. It's used in plasma simulators for these like tokamak reactors. So it's used in science. It's used for things like climate modeling. And we really like that JAX is used not just for LLMs, but really for all kinds of numerical computing. Exciting stuff. So what is good about JAX? Why are all these projects using JAX? It's because JAX has AGI. AGI is awesome scalability, great expressiveness, a little bit of a forced acronym, and incremental composable control. I think this is what people are excited about when they say AGI. And it gives you this because it's a compiler-oriented system, and it has this great epic handshake with XLA. So I want to say a little bit more about this last bullet today. This is a thing we've been working on really for the last year or two, this incremental composable control. And what we mean by that is that JAX, the classic way that people wrote JAX, 5 years ago, is they just wrote the math. It's almost sort of declarative, where you write the math and the compiler takes care of how that math is actually executed on the machine. You don't really have to worry about the details. And that's still a great way to write JAX code, especially if you're in research mode, you just want to get something started, get it going. You can actually write pure math code and even scale it to lots of accelerator devices. Pretty great. But there really is this trade-off where if you have pure math code, maybe it's extremely flexible. Maybe it's portable across different scales, across different backends like TPU, GPU, CPU, etc. Maybe it's more transformable in some ways. But as you want to squeeze out more performance, you often want to specialize a bit on some details of the hardware platform that you're working on. And you may want to specialize some amount. You may want to decide, hey, I really want to control exactly how my data and compute are being distributed over my supercomputer cluster because it's very expensive and I want to make good use of it. Or maybe you want to take even more control and be explicit about how exactly the communication is happening, how the communication and compute are overlapping, this sort of thing. Or maybe you want to go all the way down and use a sort of lower level language like writing Pallas kernels, where you might be specializing on exactly the generation of GPU that you're on and use sort of generation specific features. So what we're trying to do with JAX is not force you into one way of operating, but really let you choose what point that you're operating on in this trade-off space of sort of flexibility and direct control. And we want it to be incremental in the sense that you can just take control of little pieces at a time. You don't have to do it all at once, like, oh, we have to rewrite all of our code in a low-level way. And we want it to be composable so that all these pieces work together in one project. So to illustrate what we mean by that, I have two little stories. One is about sharding. Sharding is about, hey, I want to speed up my transformer models, for example, or scale them up to be much bigger. How do I throw chips at that effectively? Or how do I throw chips at my problem to make sure that serving is really fast so my users get a great experience? So I'll just talk a little bit about how we might shard a simple dense transformer. This is like a Llama 3 style architecture, and I'll just talk about this MLP block down here, which just has a few matmulls. I'll even remove that sort of gating einsum matmull. So really what we boil down to here is matrix multiplies and how to do them in a distributed fashion. So here in this picture, we have these rectangles representing arrays, and we have their shapes sort of annotated here. These, B of 16 with their shapes, B by D or D by F, and then the arrows represent data flow, and the red X's represent these matrix multiply operations. So let's say that your model is so big you can't even fit it all on one device, like all the layers, all the parameters. You can't keep all of those things on each and every device all the time. So let's say that you want to store the big weight matrices in a sharded way over your set of devices. So the way we're going to think about sharding is we're going to think about having all of our devices in an n-dimensional array of devices. Here it's just one-dimensional, so we think of our GPUs arranged in like a 1D line, and we're going to name all the axes of that grid of devices. And in this case, we're just calling it capital X. And so when we say we shard up the weights, I'm going to use this notation here where we, in the sort of shape, we write this little @x to say this array axis is sharded over this mesh axis X in this way. And the colors correspond to how the data is distributed. So let's say you have a big model, you've sharded the weights. Now you have to wonder, okay, how do I shard all these the activations flowing through the model? And there really are some choices. So for example, maybe one engineer says, oh, I know what to do. I've been working on like pre-training, and this is easy. You've got to do FSDP, fully sharded data parallelism. So here's what we do. We're going to shard the batch axis of our activations this way. And the way these matrix multiplies are going to work out is we're going to all gather the parameters just in time and then do the matrix multiplies, and things stay sharded this way. That's great. And then some other engineers like, no, you fool, like you're not thinking about low latency decoding. What we really need to do, we don't have time to like move these parameter matrices around so much. What we really want to do is some tensor parallelism where we actually have the input activations replicated over all of our devices. And in the first matmul, there's no communication. And in the second matmul, we're going to have to do an all reduce to get our answer. And then a third engineer comes up, and she's Dora the Explorer, and she says, "Porque no los dos? Let's do a mixture of the two." And that's surely got to be better. So we're going to have a 2D mesh and shard our activations and our parameters this way. So, what do you do? How do you choose? So one option, JAX gives you options. One option is like, shut up. I don't want to think about this right now. I'm in research mode. Just let the compiler figure this out. I'm sure it has, heuristics that'll do decently well, and I could get some initial results. So that's this sort of like automatic sharding mode that JAX has. And here's the way you would write the code for this. It looks like the code on the first slide. You write your dots and your nonlinearities, and all of this is sort of a global view of your computation where you don't even think about the fact that you're running on multiple devices. You're just writing, here's how the math works, and the compiler is going to decide how to shard up these pieces and lower things to insert communication across devices as needed. So we're not thinking directly about sharding very much. We're not even, not writing collectives. This is this automatic mode. We are actually really excited about this other mode because people care so much about performance. Another mode you can switch into is called explicit sharding or sharding in types. And my colleague here made this logo, which I think is like some soft serve or something, sharding in types. You can guess the acronym we use to refer to this project internally. So this sharding in types mode is a bit different. Actually, you could see the code here is pretty similar. It's still high level, still a global view. We're still thinking about matrices and not about sending communication between devices. But here, the idea is that the sharding is carried in the types. So just like you can reflect on the shapes of your arrays, you can print out the shapes of your arrays. You can also print out the shardings. And as a result, your code, it's always clear at sort of trace time what all the shardings of all the data is going to be. And JAX will actually error if you ever encounter a place where the sharding, like how the result should be sharded, is ambiguous. So in the automatic mode, if you write something and the compiler's like, oh, I don't know what to do. Like, it's not clear how this output should be sharded. It'll just use some heuristics to fill it in, and it might do some heroic communication to make that work. But with sharding in types mode, you get an explicit trace time error if there's ever any ambiguity, and so the JAX system forces you to decide how things should be sharded. And this is really a great mode for performance work if you're trying to decide between sharding strategies, because it lets you flexibly change your mind about how sharding should be, but at the same time, there's no surprises, there's no compiler making these decisions for you under the hood. So we call this explicit sharding. This is actually how you'd write the code for this sharding strategy. But if you just tweak the code a little bit, basically annotating the out shardings on the matrix multiplies, you can get these other sharding strategies as well. This could be config driven or just iteration based. Great for performance work. And we do have this third mode, which you may know, which is called shard map, which you think of as like, this is when you're dropping into sort of a per device view and writing explicit communication across devices. Maybe you want to do this if you want to be really careful about how communication and compute overlap is happening. If you want to pipeline this, gather with the matrix multiply, or you want to make sure it's happening, during your previous layers flops. Or if you want to be really careful about numerics, you might drop into this sort of manual mode. So we have this whole grid of, how explicit are you being, how much control are you taking of your sharding, and how much do you write versus how much do you let the compiler take care of. In fact, it's not just that you switch between these modes like all at once. You can actually have over your mesh, every mesh axis can be in a distinct mode, if you like. So you could be sort of have manual mode for your pipeline parallelism axis, where you do the pipelining with explicit collectives, and at the same time be sort of in sharding and types mode for your tensor parallelism. So you can really mix and match all these things. That's how you write all these things in JAX, but then it's like you still have this big design space. How do you think about how do I make use of my compute resources efficiently? So there's this great book, How to Scale Your Model, sometimes called the TPU scaling book or the JAX scaling book. It's this online resource on TPUs. It also covers GPUs as well. And this goes through in all the detail how to think about your hardware and sort of roofline analyses to decide how to efficiently shard things. It uses a mathematical notation, which has essentially direct correspondence to these JAX APIs, these JAX types that you see. And there's this other repository, JAX LLM examples, which is basically like the real code version of all these ideas. In fact, to say a little bit more about that, this repository has sort of pure JAX minimal implementations, minimal yet performant on TPU and GPU of all kinds of open source models like DeepSeek or Kimi or Qwen or GPT-OSS. So it's really a great resource. It even has things to do with like serving. So if you want to learn about high performance serving with like a minimal example code base that's still performant, it'll teach you about KV cache management and continuous batching and things like prefix caching. It's all in there. It's a great little repository, especially if you want to learn. There's also this, in terms of learning resources, this is a great project called Bonsai, which has a whole bunch of example models as well beyond just LLMs. So that's one story about how we're trying to give you more sort of incremental control. Here's another story about kernels. Let's say you want even more control. You're like, okay, I've taken control of like how my distributed compute works, but what if you want to take really fine-grained control over what your devices are doing? You want to say, how are my devices chunking up my data into tiles and then processing those tiles, pipelining them through the memory system? So what if you want to be explicit about where data lives in different memory spaces and how those transfers are happening? You want a kernel language, and JAX has this phenomenal kernel language built in. We call it Pallas. Let me give you a whirlwind tour because it's easy enough that actually you can see how to use it in just a few slides. So here's like a hello world kernel in Pallas. We're just adding to, let's say, matrices, like 2D matrices. The basic idea when you write a kernel is you write a function that takes in shaped array references. So these are different from regular arrays because what you can do to references is basically you can load from them and store to them. And this is going to model like the memory accesses that you really want to be explicit about when writing low-level code. So here we're loading from these two references to get sort of immutable JAX array values. Then we're doing the usual JAX NumPy math, like adding things, and then we're storing the result back out. And the way you interface this kind of code, which has explicit mutable array references coming in, the way you interface that with the rest of JAX is use this Pallas call or tor map. Pallas call is the entry point to think about. So we sort of turn this kernel function into a JAX function with pure array values in and out by using Pallas call. So this doesn't have any parallelism in it. The way we start getting parallelism, when we want to use our device effectively, it's got a lot of parallel compute. We want to launch multiple parallel instances of this kernel. And the way we do that is we just add this sort of grid argument. Here we're just saying, launch a bunch of instances of this compute, and each one is going to work on a piece of the input. Here we're just slicing out a piece of the input explicitly. There's a problem with writing code this way though, which is that these HBM accesses or global memory accesses are very high latency. And so they're slow, basically, compared to your compute. And if you write code this way on classic GPUs, with simpler programs like this, you can actually, the GPU can hide this high latency memory access. It can hide it basically by sort of cheap context switching. So you can launch all these kernels, and then the GPU will automatically context switch to hide the memory latency. But this isn't such a great way to write code on modern GPUs and TPUs because all the flops are in these big matrix multiply units, and to drive them, you sort of really need a lot of context, and you can't do cheap context switching. So this is not a good way to write kernels on modern GPUs and TPUs. What do we do instead? So here's another toy example, a matrix multiply, which will show you what we do to tackle this problem. Again, we have a very simple kernel that's loading from references, doing some math and storing. And now we have this Pallas call, and we've added these in specs and out specs, these block specs. And what this is doing is these are going to describe to this Pallas call how it can do software pipelining for us to hide the memory latency. So let's look at how that works. So we still have this grid. In this case, it's a 2D grid of program instances. And then what these block specs are doing is saying, how do we tile up these inputs and outputs? So for example, it's saying the left-hand side of our matmul, let's chunk it up into block rows, the right-hand side into block columns, and the outputs into these little blocks. And then this part of the block spec is saying how each program instance will load and store data, how it touches the data in the operands. And by writing the code this way, now you've given Pallas all the information it needs to do software pipelining behind the scenes, meaning it'll be launching asynchronous memory operations and hiding that memory latency behind pipelining. So that's whirlwind matrix multiply. Here's a flash attention, slightly simplified, but works pretty well on TPU. Don't try to read every detail, but the point is that it fits in a slide, and you can even do neat tricks like VMAP these kernels sometimes, when they're written this way, to get things like multi-query attention or multi-head attention. Some JAX transformations even work with Pallas kernels. So recently, our team has been doing a lot of work on adapting Pallas to give it features to target these brand new Blackwell GPUs and really drive them at sort of speed of light. And Adam had this tweet recently about this this tutorial that he and the team wrote, which again, if you just want to learn how Blackwell GPUs work, this is a good way to do it. It walks through all the fancy GPU features you need to really get the maximum performance, like warp specialization and persistent kernels and all the tiling patterns you need. So that's pretty fun. You've seen tutorials like that maybe from other languages, but again, what's special I think about Pallas and this Mosaic GPU backend is it really is terse. And again, we're not going to go through every line of this kernel implementation, but this is actually like a speed of light Blackwell matrix multiply that fits on a slide. It's very information dense, but it's that's sort of a good thing. So actually, when Adam tweeted about that, someone asked like, "Hey, when is the TPU tutorial coming for doing high performance matmuls?" And he said, "It sounds like a joke, but actually we didn't write a tutorial because this like 7-line kernel gives you the state-of-the-art matmul performance on TPUs. It turns out if you build a machine that is really good at matrix multiplies, it's easy to tell it to do matrix multiplies. So there's even tutorials on TPU and on GPU on how to do sort of communication operations in the kernels efficiently to do things like distributed matmul. Super fun. So in the last couple of minutes, I'm just going to talk a little bit about some new ways to take control that we're working on. I only have time to mention one of them. And this is about a new way to extend JAX. So when you want to extend JAX, today you sort of have two options. Let's say you want to add a new type that works with JAX. You kind of have these two options. You have PyTrees, and people do all kinds of things with PyTrees that weren't planning on people using PyTrees for. But PyTrees, they're very lightweight as a way to sort of teach JAX some basic things about your data type. But you sort of can't say very much, actually. Like PyTrees are very, very limiting. They're lightweight, but very limiting. And then there's JAX internals. It says here be dragons. JAX internals are made to be extensible. You can add types to the JAX system, but very few brave souls have ventured to try this, and even fewer have returned to tell the tale. So the question has arisen: is there a third category of extension point for JAX that we can add? And I think if such a third category of extension point were to exist, it would have to be far better at some key things, like it would have to be better at introducing new types, as well as introducing new primitive operations that might work on those types, consume those types. It would also need to let people control very precisely like how those types interact with autodiff. Maybe you have a quantized array type, and you really need to specify how autodiff interacts with it. We need a way that's lightweight that you can tell the JAX system about your quantized array type and how it works. And maybe even we should add in a way that you can describe mutability that all lowers to sort of pure value semantics under the hood. So we have we're working on such an extension point. It's experimental right now. We call it Hijax. Be careful if you flew here. Don't talk about this feature when you're like flying home, because you'll get stopped at the airport if you talk about this. So it's just a brief taste of Hijax. This is what it looks like if you want to introduce a new type, like a quantized array type. Here we're just using a data class. There's nothing JAX specific about this. And down here we're creating something that represents the type to the JAX system, if you want to put this in JAXpers. And I guess a key detail here is the way we're interacting with autodiff. We're actually able to say to JAX, hey, this is my quantized array type. When you differentiate with respect to this, the gradient type associated with it, or the tangent type, actually shouldn't be another quantized array. In this case, maybe you want it to be a dense, float32 array. So you can write code with your quantized array. When you differentiate it in the backward pass, it'll all be, dense float32 stuff. So if you want to express something like this, Hijax gives you an easy way to do it. And then here's how you can introduce operations. This is, introducing this primitive. I won't go through all the details, but basically you tell JAX how to expand your operation into sort of lower level operations and how it should interact with autodiff. In this case, it's just a quantization, so it's a very simple interaction with autodiff. But at a high level, this is what we're working on with Hijax, and I think you'll hear more about it in Christian's talk about NNX later today. So that's all I have. That's JAX. I'm so excited about all the things you guys are using JAX to build, and I'm really looking forward to hearing all of your thoughts today. So thanks for coming.